All right, so in this video, we're going to continue talking about improper integrals and take a look at another example here. You can see that in this setup, we do have our negative to positive infinity. And so we'll have to set this one up by breaking it apart into two different integrals. So the first one, we'll start with a limit as t goes to negative infinity from t to somewhere else. And I'm going to come back to this guy here in just a minute. Then we'll have our e to the negative x over 1 plus e to the negative 2x dx plus the limit as t goes to positive infinity from somewhere, which again I'll come talk about in a moment, to t. So I'll plug my t in there, same function, and then followed by our dx. So much like in Calc 1 when we split up our region, we just need to make sure that this number and this number are the same thing. And earlier I said it's not a random number, but a lot of times you can pick whatever you want, assuming it's not going to make your denominator 0 or cause any concern in the original function. And in this case, there really is no concern, so I would pick an easy number. I would pick a 0. So that's by choice. But again, it's being chosen knowing that it's not going to cause any harm in the function. It's not a discontinuity of any form. Okay, so now we're ready to integrate, and technically these are both the same integrals. We're just evaluating at different places, and so no real need to work this thing twice. But either way, it's going to be a u sub. We're going to let u equal e to the negative x, du would equal negative e to the negative x dx. And then as I change notation here, once again, we're changing variables. So I'm going to be pretty careful here. I'm going to have my negative that I went ahead and moved around and pulled out. Then I'm going to have my limit with my integral, 1 over 1 plus u squared du. And remember, I'm not putting anything there because I've changed from x's to u's. And these are x's, and then if I change there, this guy right here would be irrelevant. So I'm just going to leave those blank. Then I'm going to have minus another limit, leaving it blank, integral, 1 over 1 plus u squared du. Now again, I realize that if I were to just throw this at you separately, you would say, well, that's negative 2 of those things, right? Well, remember, there are different bounds here, so we're kind of working this step by step. So let me go ahead now and continue the integration. So we'll have a negative limit, t goes to positive infinity, inverse tan of e to the negative x, being evaluated now t to 0, minus the limit, t going to positive infinity. I'm going to circle back here. This guy right here should be a negative. I apologize. That's a negative infinity there. And then we'll have our inverse tan of e to the negative x being evaluated from 0 to t. Okay? So again, what we're doing here is mostly in the notation, and there's a little bit of subjectivity in how you want to show this, but what I really want to emphasize is not writing the t and the 0 anytime you have anything other than x's like we do here, and so just be a little bit careful there. Okay, so let me go ahead and expand this all the way out. This is going to be negative limit as t goes to negative infinity. We would have inverse tan. And if I plug my 0 in, that's going to be a 1. So we put our 1 there, and then minus inverse tan. Now we have an e to the negative t. And so at this point, hopefully you guys are seeing what the advantage is and why we have to introduce the limit. I wouldn't just be able to plug an infinity in right there, even though we kind of talk like it. Mathematically, the notation is not acceptable. And then we have minus, and then a pretty similar thing. Limit as t goes to positive infinity, inverse tan e to the negative t, and then minus inverse tan of 1. All right, so now we're ready to come through and evaluate. So the inverse tan of a 1, we all know is pi over 4. And then over here, if I take this negative infinity, and I take this negative big number and I plug it in here, the double negative is going to make it positive, which means I have e raised to a really, really, really big positive number. So as this argument here for the inverse trig function goes off to infinity, our inverse tan limits at pi over 2. So we have our minus pi over 2. And then this negative that I just included was this guy right here. Okay? And so then we have our minus, and very similar argument. As t goes to now a positive number, when I plug that in, because our really big positive number is plugged in here, but with that negative, it's going to flip it around. That's the conversation we had before, where that was essentially the 1 over e to the t, which clearly would go off to a 0 as we approach infinity. So that would be a 0. And then once again, we have our pi over 4 from our inverse tan of 1. So to save a little bit of room, I'll come to the top here. Looks like we have a minus pi over 4, plus pi over 2, and then plus pi over 4, giving us a pi over 2 for our final answer, and once again another improper integral that converges. Okay, so as we take a look at our next example, you might on the surface look at it and say, well, that's not an improper integral. You've got a 0, you've got a pi over 4, all is good. But there's a little bit of a problem. If you'll notice, when I take pi over 4 and I plug it into this denominator, this is going to give me a 1 minus a 1, which is a 0. So if we view this now as the area under the curve on the interval 0 to pi over 4, well, at pi over 4, you have a discontinuity, right? You have an asymptote. And so what we're going to need to do now is rewrite this using the correct notation. So what I think best is actually drawing just a very, very simple picture. All right, we know that x cannot equal pi over 4. And we also know that what we're studying is the interval from 0 to pi over 4. So picture some graph up here, and we're finding the area under it, okay? So what's happening then is we're not allowed to get all the way to pi over 4 because we can't. It's a discontinuity. So instead, we're going to be approaching pi over 4 from the left. So the notation here that we would want to use would be the limit as t approaches pi over 4 from the left, from 0 to t, secant squared x over 1 minus tangent x dx. All right, so that's where it's a little bit hard to pick up on unless you're really paying close attention to these values here of x that would essentially define our region for the curve. So then, once we have it set up, we can integrate as usual. And in this case, it's a pretty simple u sub. 1 minus tangent x would be our u. Our du would be this negative secant squared x dx. Much like I've done in the past, my notation now will be a negative limit with the integral symbol, 1 over u du. Again, that negative there is from this guy being moved over. Okay? So then, as we evaluate, we've got our negative limit as t approaches pi over 4 from the left. Then we have the natural log absolute value, 1 minus tangent of x, all of which being evaluated from 0 to t. All right, so let me go ahead and evaluate. We've got our negative limit, t goes to pi over 4 from the left, natural log absolute value, 1 minus tangent of t. Then we have minus the natural log absolute value, 1 minus tangent 0. And so, when we evaluate now, I think I might have put some parentheses in the wrong spot. Yeah, there we go. All right, so as we evaluate now, we're going to be taking this pi over 4 from the left and plugging it in. So as I take the pi over 4 and I plug it in here, that's going to give me a 1. So we'll have a 1 minus 1, so natural log of 0. So I've got a negative and then a natural log of 0. And then we would have a minus. And this guy right here, this is 0. So natural log of 1 is 0. So that's just going to be a 0 right there. And so we're studying negative natural log of 0. Well, that's undefined, right? Natural log of 0, that's the asymptote, the vertical asymptote. So as we approach that, we're getting a negative infinity. So we're getting a negative infinity, all right? So remember, the natural log of 0, that's our vertical asymptote. As we look at this in terms of where the y coordinate is going, it's going down to negative infinity. So we have a negative and then a negative infinity, leaving us with a positive infinity for our final answer, saying that the original diverges. So again, guys, be real careful when you see these types of integrals now. No one's really trying to trick you, but do understand that even if you don't see an infinity, that you need to investigate pretty closely what these bounds do in terms of your actual function. All right, so in this last example now, you'll see that not only do we have to be careful with the bounds, the 1 and the 4, but we also just have to be careful in general of what's happening in our picture. And so 1 and 4 were safe, but we can see that in this particular problem, x cannot equal 2. And 2 is between 1 and 4. So we have that discontinuity now between our lower and our upper bound. So much like on the last problem, I'd recommend drawing a very, very simple picture. We know that we're interested in 1 to 4, but we also know that this 2 is here in the middle. So as we set this up, we're going to be needing to approach 2 from the left, and then picking back up and approaching 2 from the right. So let's see what this looks like. We're going to have the limit as t approaches 2 from the left of the integral 1 to t. And then I'll drop my function in here. And then plus the limit as t approaches 2 from the right. And now we'll have from t to 4, picking up the rest of the region we're interested in studying. So this guy right here, this first integral, is from essentially 1 to 2, but since we can't technically get to 2, we're going to approach it from the left. And then this second integral here is for essentially this part, where we go from 2 to 4, but because we can't physically be at 2, we would be approaching it from the right. And so there would be a setup for a problem like this. And as I mentioned on the last problem, no one's really looking to trick you on these types of things, but this does go to show you that you really have to be aware of the interval now in which we're studying. We weren't pushing this issue in Calc 1. Everything was kind of nice and simple and worked out nicely. But now we have got these cases where we are still interested in studying them, but they might not be as nice as they were in Calc 1, where we had this closed region and everything worked out as well as it did. Now we have to be very, very careful of any discontinuities, either on the bounds or within the region of study. So I'm going to leave this one alone. The integral is actually very, very simple, but it would be considered a setup for this type of problem.